Hey guys, we're on slide 16 of the chapter 6 PowerPoint. We're going to keep on moving. Last time I ended on question A of this slide where we had a photon of 430 nanometers. We switched that into meters and then we plug it into the equation E equals hc over lambda to find the energy. Now we're going to continue on and say, okay, what if we wanted to know for that photon what was the frequency of the light? Again, it just comes down to being comfortable with the equations. So the equations I have on the board here, the first equation was E equals hc over lambda. Using that equation, we started with the wavelength. Now we know the energy from part one. When we go to the second part of the equation, we want the frequency. At that point, if I've already found the energy, I could plug in the energy in Planck's constant to find the frequency. That's one way to solve the problem. Or since I also know the wavelength from the very beginning, I could plug in the speed of light and the wavelength to find the energy in that equation. Okay. Again, there's two ways to get the answer. Should get the same answer either way. It may be worth your time to plug in both ways and just prove that you have a good handle on these equations. But I'm going to move on from there and let you guys solve that yourselves. So moving to slide 17. So in this question, this is a demonstration of the photoelectric effect, where essentially if we shine a light onto a metal surface, if the light contains enough energy, then it will make electrons leave their orbits around the nuclei of the atoms. When we shine the light on, if the photons have enough energy, it'll make those electrons fly out of orbit and fly away. Okay? Now, there's a minimum amount of energy that has to, each photon when it hits the atom and is absorbed, if it has enough energy, then it can make the electrons fly away. So in letter A, we want to calculate what is the minimum energy that will be required to eject an electron, given in the question that they gave us the frequency. So we know the frequency, we have to solve for the energy. So I've already worked this out on the slide. I'm going to use the equation E equals h times nu, which is one of the ones we've shown previously. H is Planck's constant, 6.626 times 10 to the minus 34th. Frequency is 1.09 times 10 to the 15th. That was given in the problem. If you watch our units, joules times seconds are the units of Planck's constant. Seconds to the minus 1 are the units of frequency, which hertz is seconds to the minus 1. Well, seconds times seconds minus 1 cancel out. That gives me my energy in joules. If you do this yourself, you should get 7.2 times 10 to the minus 19 joules. That's a tiny number, but just keep in mind, photons are tiny little bits of energy, so we expect to have a very small value for our power of 10, okay? Now, if we go to letter B of this question, when we shine a light onto the surface of the metal, molybdenum in this case, we're usually going to have more energy in the photons than we need. Okay, it's kind of like if you go shopping and you're expecting to buy $80 to $90 worth of groceries, you have to go to the store with more than you expect to spend. So you go to the store with $100, spend $80, but when you go home, you're still going to have $20 left. Okay, well, letter B, we just figured out the amount of energy that it's going to require to get the job done. But when we shine a light on it, we need to make sure the photons we shine are going to have more energy than what's required. Now, what happens to the extra energy? Well, when the electron absorbs the photon, it gets the whole package of energy. It's going to use part of the energy to escape, and then the rest of the energy is going to determine how much kinetic energy the electron has when it flies away, meaning the more extra energy it has, the faster it's going to be moving, because kinetic energy is related to velocity. Okay, so if I want to calculate the kinetic energy of the electron when it's leaving, I know how much energy it's going to require. That's what we calculated for A. Now I need to calculate the energy of my photon that I'm shining. It's a photon of light with a wavelength of 120 nanometers. So I'm going to plug that into the equation. again, I've already done this on my board. The energy of the photon equals hc over lambda is my equation. Planck's constant times the speed of light over the wavelength. The wavelength needs to be in meters. Plug all that in, and you should come out with the energy of that photon is 1.66 times 10 to the minus 18. So the photon that strikes the electron and is absorbed is 1.66 times 10 to the minus 18 joules. If you recall a minute ago, we only needed 7.2 times 10 to the minus 19. So from the amount that I'm giving, I'm going to subtract the amount that's needed, and the difference between those will tell me how much is remaining as the electron flies away. That'll be the kinetic energy of the electron. Okay, so I've already done the subtraction between those two, and I found that the value was 9.365 times 10 to the minus 19 joules. Okay, again, I didn't really pay attention to sig figs, which of course you should, but it's around 9.4 times 10 to the minus 19. Okay, so now we keep going. The next topic related to the development of understanding how light and electrons interact is the phenomenon of emission spectra. The idea of this is when we take different types of light sources, we can look at the light from the sun, we can look at the light from a light bulb in the classroom, we can look at light from a neon light bulb. Okay, so if I have a light bulb filled up with neon gas, once we turn that light bulb on, it's very remarkable that we get different colors and different wavelengths from each source of light that we look at. The reason that's remarkable is that if electrons could randomly, like an electron that's orbiting around a nucleus, the orbit that it's in requires the electron to have a specific amount of energy. If it has too much energy, it'll fly away. If it doesn't have enough energy, it would crash into the nucleus. So in order for an electron to be in orbit, it has to have a very specific amount of energy to maintain that orbit. If the electron gains energy, it has to jump into a new orbit further away and establish a new orbit in that position to balance out the attractive force in the nucleus and the centrifugal force to make it fly away. If you get those things balanced right, that's when it actually establishes an orbit around the atom, around the nucleus of the atom. Now, if electrons could go from one orbit, if they could absorb any amount of energy and jump into a new orbit, if there were no rules for all that, then basically what would happen is all light sources, which what a light source is, you have a bulb filled with a gas or some element, you apply energy, and the electrons in the atoms start jumping up and down in different orbits. When they absorb energy, they jump up to a high energy orbit. Then when they get there, they want to drop back down again. When they drop back down into the low orbit, they emit a photon of light. That's what causes a light bulb to turn on. Okay? Now, electrons can do that over and over again. Every time they absorb energy, they jump up. When they emit a photon, they drop back down. And then with a constant flow of electricity, they just go up, down, up, down, up, down. If you get millions of electrons doing that, then that's what a light bulb is. Okay? Now, if the electrons could jump into any orbits they wanted to, then that would mean I would get a mixture of all colors of light, and every source of light would end up being what we call, on the next slide, it's called a continuous source. A continuous source is the flashlight in this example, or if I take light from the sun. If I send the light through a slit, which just gets all the light to be parallel and moving in the same direction, and then I send it through a prism, we all know that when you send light through a prism, it's going to separate out all the wavelengths into the component colors. A continuous source will contain all the colors of the rainbow, will all be represented once you send it through the prism. Okay? Now, if I look directly at the source, my eyes can't see all the different colors. If I look directly at the flashlight or look at the sun, I'm going to see the average color, which is kind of a yellowish, white or yellow light that contains all the colors. I can only see the components if I can actually separate them out using a prism or something else called a diffraction grating. Okay, but some sources of light contain the whole rainbow. If, however, so that's what a continuous spectrum is. If I turn on a neon light bulb though, which is a light bulb that's filled up with neon gas, if I turn, we saw it on the previous slide, if I turn on a neon light bulb, what I notice is, number one, the color of the light from the source is different. Neon light bulbs are always kind of a reddish orange color. And then when you send the light from a neon bulb through the slit in the prism, I don't see the whole rainbow. If I look at a neon source, I'm only going to see this bottom row. These are the colors that are present in the light that comes out of a neon light bulb. Okay, now specifically, they're all lines because when I send all the light through the slit, and then when it diffracts out, I'm going to get very specific vertical lines of light that come through. Okay, and each line represents a different wavelength of light that's being produced in that light bulb. Okay, now if we remember earlier, I mentioned the different shades of colors. So like right here, there are two different lines of blue light. That represents two wavelengths that are close to each other, but they are different. So this would be two different shades of blue that have a wavelength of around 465 to 470 nanometers. Then I have some green. There's three different lines of green that are all around 480 nanometers in wavelength. Then I have yellow and several yellow lines, and then some orange lines, and then some red lines. Okay? So these are the only colors that will come out of a neon light bulb. And it's always the same. It doesn't matter if the neon light bulb is, if I turn one on in the United States, or if I turn one on in China. It doesn't matter if the light bulb was made in the United States or made in China. Doesn't matter. Neon light bulbs always give off the same set of colors, and they don't give off the whole rainbow. That's crucial because it tells us that when we take a neon atom and we give it energy, and the electrons go from whatever orbit they start in, when they jump up to a higher energy orbit, there's a very specific set of orbitals that the electrons are allowed to be in. Because if the electron jumps up to the higher orbit, when it drops back down again, that's when it emits a photon of light. Well, the difference in the energy levels is going to correspond to a certain wavelength. And there's a certain number of energy levels that are allowed. And every time an electron drops from a higher one to a lower one, there's going to be a characteristic wavelength that's emitted that's going to match up with these colors. Okay? So that kind of helps scientists start to realize only certain energy levels are allowed, and for each element, they're different. The wavelengths I get from a neon light bulb are very different from the top line is hydrogen. If I look at a hydrogen light bulb, there are only 4 colors that come out. So that means there are only 4 energy level transitions that give us visible light. Now there are other transitions that can occur that could give us either ultraviolet light or could give us infrared light. Okay, so we can go outside of the visible range. But within the visible range, there's a limited number of electronic transitions that can occur. That's going to lead us into a bunch of math that we're going to do in a little bit. Okay, so that brings us to Niels Bohr. He kind of took these concepts. He said that, okay, for each electron, he looked specifically at hydrogen. N equals 1 represents for a hydrogen atom, which has 1 electron in it, the lowest energy orbit that an electron can be in, which is really close to the nucleus. The electron's flying around. That orbit, the amount of energy it takes, corresponds to this line. Okay, so vertically we're increasing the energy. So N equals 1 is the lowest energy orbit. And then if we give it some energy, we can make the electron jump into the second orbit, n equals 2. Or if we give it more, we can get it to n equals 3, n equals 4, n equals 5. As you notice, as we go to higher energy levels, they actually get closer together. And there are an infinite number of energy levels that you can go to, although if you go above the dotted line, that's where the electron has enough energy to escape the atom. Okay? So we have specific orbitals that are allowed, and an electron, if it gains enough energy, it can jump from a low orbit to a high orbit. Once it gets to a high orbit, if it wants to come back down again, it has to emit a photon. So Niels Bohr kind of developed all these rules. Rule number 1 is that an electron can only be in a certain orbital that's allowed. Okay, only allowed orbitals can exist for the electron. That's rule number 1. Rule number 2, if an electron is in an allowed orbit, then it's going to maintain that energy until it can go to a new orbit. And what that means is it's not going to like gradually lose energy, and like with a satellite in space, if you leave a satellite up in space for enough time, eventually it'll crash down to the Earth, because just over time, every time it interacts with the atmosphere, even the upper atmosphere where there's not much air, friction is going to make it lose speed. As it loses speed, eventually satellites crash. In an atom, there's conservation of energy where the electrons are moving around. Most of the atom's empty space, so there's no friction or anything. So basically, Bohr assumed that the electron's going to stay in orbit forever as long as it doesn't do anything else. Okay? It'll never just give up energy and crash to the nucleus. He made that assumption without any real mathematical proof. He just said that has to work, or otherwise nothing else makes any sense. Okay? And then number 3, the only way it can switch from one orbit to another is to absorb the right amount of energy to go up, or to release the right amount of energy to come back down. Meaning, to go from n equals 1 to n equals 2, there's a specific energy difference here. It has to match up. An electron here has to absorb the right amount of energy to get to here. It can't go halfway and establish a new orbit right here. It can't go a little too far and establish an orbit here. It has to go to the right spot, so only certain transitions are allowed. It's absorption of energy to go up, and if it drops back down, that's when we emit a photon of light, which if it happens to be visible light, that's when we see a color. Okay, so those are Bohr's 3 rules that he set up for his model. I'm going to have to cut off the video, and we'll continue on in the next one.